All right, team. Next thing we're going to do, you've done it in Calc 1. It's just the same thing, implicit differentiation. Okay, so implicit differentiation. Let's just review our memory from Calc 1. Let's say you have, so this is a, oh, never had that happen before. Calc 1 refresh. Okay, let's say you have some function of x and y equals c, okay, and you assume that there is a relationship between y and x. Okay, now this is actually, you don't actually have to assume it. This is a relationship between y and x, okay? It's just not explicitly defined. It's called implicitly defined, okay? And you can find the derivative of y with respect to x this way. I'm going to go, you could have seen this in a Calc 1. I'm going to go a little more in depth than what you might normally see. But let's go ahead and take the derivative of both sides of this equation with respect to x. I'm going to write it like this. Okay, so now we are using partial derivatives. Okay, so that's why we can talk about it a little bit more in depth than we did in Calc 1. Okay, so we could write this as, this is the partial of f with respect to x plus partial of f with respect to y times dy dx. That's the left-hand side. Okay, so you see this just depends on x, right? This depends on y, but that y dependence has an underlying x dependence, and that equals 0. Okay? So then, dy dx equals negative partial of f with respect to x divided by partial of f with respect to y. Okay, so let's do an example that you would have seen in Calc 1. Okay, so as an example, let's take x squared plus y squared equals 1. That's just a unit circle. Okay, let's take and suppose y is a function of x. We don't really suppose it. It's more like we're just saying that we're going to use x as the independent variable. We could also do it the other way around. Okay, so if we do that and take the derivative of both sides, and this you would have done in your Calc 1 class. You would have said, okay, that's 2x plus 2y, and then you're going to go, oh yeah, there's a y prime here equals 0. So y prime equals negative x over y. Okay, all right. Little bit sketchy there. Okay, there's some stuff I don't like there, but I want to show you something more. Okay, because now we're in Calc 3. We can just make sure that's right. We can do a lot more than that. Okay, let's take a look at x and y values that actually do this via like parametric equations. Okay, let's consider x equals cosine t, y equals sine of t, right? So now, we did in the section on parametric equations, we took dy dx, didn't we? Dy dx is dy dt divided by dx dt. Okay, let's take dy dt. Dy dt is the derivative of sine of t, is cosine of t, divided by the derivative of cosine of t, negative sine of t. Let me write that a little bit better. Negative sine cosine t over sine of t. Notice, I want you to see this. dy dx is the negative of x divided by y. Interesting, huh? Okay. We could also do this for now in higher dimensions. Let's say we have f of x, y, z equals c. And we're going to take, now in this case, we're going to say, all right, if we have this, remember, this is a three-dimensional object, but it's set equal to a number, so like a sphere. Okay, that's a typical example. A sphere is really a two-dimensional object. Just like a curve, even though it lives in 2 dimensions, is a one-dimensional object. I've been saying this a long time. What do I mean by that? That you can define a curve by one free parameter, right? Say like a line, right? That's a typical example. It's a one-dimensional object. It's got that one independent variable, but there are those three dependencies. Similar to a plane. A plane has, ax plus by plus cz equals d, right? But really, we could always solve to make one of those variables a function of the other two. So it's a two-dimensional object. So this is a two-dimensional object by saying this. Another way of thinking about it, we have three unknowns and one equation to get rid of one of the unknowns. That's sort of a linear algebra thing that if you're interested in, take that course, okay? But what we're going to do then is we're going to take and we're going to say z is a function of x and y. We could have chosen x being a function of y and z. We could have done it any other way. That's just the normal way we do it. All right, a lot of talking, less talking, more math. Okay, so let's take the derivative of f with respect to x. Now, x, y, and I'm going to write z as a function of x and y, just to remind myself. I don't always do that, but I'm doing that now. So now, it's going to be partial of f with respect to x plus y does not depend on x. Y is another independent variable, okay? We've got two of them. Plus partial of f with respect to z equals 0. Oh, what did I forget? I forgot my dz dx. Solving for dz dx, or partial of z with respect to x, going to be just like we did before, negative partial f with respect to x divided by partial f with respect to y. Similarly, the exact same argument, partial z with respect to y is negative partial f with respect to y divided by partial f with respect to z. Let me put video 3 here because we're gonna continue. Okay, so let's do an example. There, if you couldn't pause it to get that. Okay. Let's do 2. So let's find partial z with respect to x, partial z with respect to y, and we're going to have, say, e to the z equals x, y, z. Okay, now I'm going to do it 2 ways. I'm going to do this directly, and I'm going to do it by what I just showed you. Okay? Either way is perfectly fine. Okay, directly. Well, when we're doing this directly, since the way the question is asked tells us z is our dependent variable on x and y. So we're going to assume z equals z of x, y. Okay? So, just had a minute of brain fartness there. Taking the derivative with respect to x of both sides, that equals e to the z times partial of z with respect to x, that's derivative with respect to x, equals, on the right-hand side, we're going to have derivative with respect to x is going to be, okay, y is a constant. Then we're going to use, let me do x, z, partial with respect to x. For some reason, I have to do it slow today. That's going to be z plus x partial z with respect to x, okay? So what we're doing the product rule here, okay? Derivative of x is 1 times z. Z, remember, is assumed to be a function of x and y, okay? Plus x partial of z with respect to x. So we're going to just expand that out. We're going to add a y on everything, so we're going to get yz plus xy partial z with respect to x. Now we're going to solve for partial z with respect to x. Do this a lot. I sort of say, okay, I'm going to move. In my mind, I'm moving all the partial z with respect to x terms over to the left-hand side. So that's going to be e to the z minus xy. On the other hand, we're going to have yz. Okay? So partial z with respect to x is yz divided by e to the z minus xy. Okay? Now, that's directly. You can do the work for partial of z with respect to y. It's pretty much exactly the same. Okay, there's a symmetry here. X and y are interchangeable. Okay, that's another trick for multiple dimensions. So I'm going to interchange them. Okay, but now let's do this same problem using the formula that I gave you on the other one. So let's look that up again, right here. Let me highlight those so that you know where to see them. Good thing I didn't have anything dangerous on my computer today. Not that I would ever do anything dangerous on this iPad, because they pay for it, not me, so won't do that. Okay. All right, so we're going to do this way. We're going to say, okay, let f of x, y, z equal e to the z minus x, y, z. I could have also done x, y, z minus e to the z. It's not going to make a difference. So our equation, we have f of x, y, z equals 0 is our implicit equation. Okay, so now let's take the negative partial of f with respect to x divided by partial of f with respect to y. Okay, so that's going to be negative partial of this f with respect to x. What's that going to be? Yz. Divided by partial of this f with respect to, why did I put y? That should have been z. Did I write that right? Yes, there. I did not write it correctly there. Again, I need to focus better, but you can see that it was like that anyways. Okay. I know some of you are trying to get extra credit there. You're like, oh, but no, I caught it before you did. Okay, so derivative here with respect to z is going to be e to the z minus xy. And this is, of course, if you look, this and this are the same. Okay, so that's the benefit of thinking in terms of generalities sometimes. All right? All right, that's all I have for you for the chain rule. I'll see you all in the next set of videos.